Improving efficiency with memoization. Alrighty, so now we are going to find a problem. And here is our problem. We are going to copy this code, which computes Fibonacci, and we're going to call test fib. And test fib, it's going to time calls to fib of n, where n just keeps growing larger and larger. And we'll see how long it takes to call fib of n. That's all that's going on here. We paste this, and what could possibly go wrong? Well, we run it, it's fast, and it's less fast, and it's less fast. And by fib of 33 on my machine, we're up to about 2 seconds. By fib of 34, about 3 seconds. By fib of 35, about 5 seconds. And in fact, fib of 36 is going to take about fib of 35 plus fib of 34, the sum of these two, so about 8 seconds. There it is. The next one will be about 13. So what's fascinating is the runtime of fib of n is about somehow related to fib of n. It's really cool stuff. But what's not really cool is this is taking a very long time and it's completely unacceptable. And a little bit of consideration will show us why that's the case. So when I call fib of 4 we said called fib of 3, which calls fib of 2, which calls fib of 1. And fib of 1 returns, and then fib of 2 calls fib of 0. So far so good. Then fib of 2 returns, and fib of 3 calls fib of 1. The fib of 3 returns, and fib of 4 calls fib of 2. And now we're starting to see a problem. Fib of 2 calls fib of 1, and fib of 2 calls fib of 0. So here's the problem. The problem is fib of 1 is being called over and over again. Fib of 2 over and over again. You say fib of 3 only once, but that's because we're doing fib of 4. What if we were doing fib of 5? It would call fib of 4, and when that was done, immediately it would call fib of 3. And all this work inside here would have to be done again right inside here. What if I was calling fib of 6? It would do all the work for fib of 5 and then all the work of fib of 4. So what's happening is work is being done over and over and over and over again. Consider how horrible this gets because fib of 39, to compute it, it first calls fib of 38, which took 21 seconds. And as soon as that's done, it calls fib of 37, which is 13 seconds, even though fib of 38 had to already call fib of 37. So these are being called over and over and over and over again. And nearly all this time is being lost to redundant work. Because if you think about it, you really only have to compute each value once. What would happen if when we called fib, we remembered the values of the result? So when we call fib of 37, we remember that that's this value here, that 39088, etc. So the next time we call fib of 37, we don't have to compute it. We just return the 39088.169. That's called memorizing. And sadly, it's not called memorizing. I don't know why, but the R is not used. It's called memoizing. Yes, that's what it's called. And so what you can do, here's your solution, is you can memoize results. You store your results in a dictionary. When you call your function, you say, hey, have I seen this before? If that is in my results, I'll just go ahead and return it. If I haven't seen it before, I have to go compute it recursively, but then before I return it, I will remember the result, so the next time that I call this, I will in fact be able to return the remembered result. Remember how long it took to compute all those values? Watch this. We copy, we go here, and we paste, and we run, bam. 0 milliseconds is very fast. I'm thinking it's lying, and it actually took some fractional amount of milliseconds since very few things run instantaneously, but darn fast. So this actually was a thing of beauty, and it solved the problem. It turns out it's an almost beautiful solution. What stops this from being beautiful is the fact that as we've written it here, fib results is a global variable. That's not so great. So there are different ways around this, and one way that we're going to do is by using something called a function decorator, or just a decorator. You are not going to be responsible for how the decorator works, but what it's going to basically do is automatically create one of these dictionaries for us and wrap it around with functions. What you do is, here's the decorator, you have to include this function in your code and maybe try not to look at what it does. But what it does is it creates a dictionary, and then it wraps. See that word wraps? It wraps your function, and it does this check to see, hey, have I seen this before? If so, I'll return the result. Otherwise, if I haven't, I'll go ahead and actually, if I've not seen it before, I'll remember the result, pardon me. And then no matter what, I'll return that remembered result. Now here's the key. Once you've pasted this into your code, to memoize a function, all you have to do is say @memoized in the line before it. And let's show that this actually magically works. We'll copy this code and we'll go, pardon me, into here. And we will paste the code. And instead of 40, let's only go up to, say, 34. And let's not memoize. So I'll get rid of that memoize. And we see we are slowing down. And now I will go ahead and memoize the code. And now memoize, bam. So certainly that, turning on that memoization certainly did the desired effect. And what it's doing is creating this dictionary and storing the results of the call in the dictionary and only calling if we have to, if we haven't already stored the result. And that is memoization. You should note, by the way, that memoization is not a very common technique. You only need it in certain rare cases. It just happens that Fibonacci fits perfectly. The reason is because fib calls itself twice on each recursive call, it turns out to do a massive amount of extra work. And the other thing is fib of n never changes. So fib of 7 is always fib of 7. If that weren't the case, then you couldn't really cache the result. So there you go. It's a trick to have in your tool chest, but it's not one you're going to use with great frequency.